putting it all together, we are now going to be able to draw and interpret potential energy diagrams. So, the important aspects of a potential energy diagram is that you have your axes labeled. So, on your x axis, you're going to put something like reaction progress or reaction pathway. And on the y axis, you're going to have potential energy measured in kilojoules. Then you're going to be able to label your activation energy, which is the difference between the reactants and the top of the bump. You're going to be able to label your change in enthalpy, which is the reaction between the reactants and the products. Like I said, reaction, I meant difference between the reactions and the reactants and the products. And then sometimes you'll actually label the actual reactants and the actual products, but that's not always necessary. So let's look at an example. So here it says, using the axes below, sketch a potential energy diagram for the reacting system where delta H is negative 30 kilojoules per mole, activation energy is 50 kilojoules per mole, and the potential energy of your reactants is 70 kilojoules. So what are we going to do with this? Well, I might start with the fact that my potential energy of my reactants is 70. So if I was to label reactants, reactants are here. Okay. Then I know that I'm going to form an activated complex if I have enough energy. And it says that the energy that I need is 50 kilojoules. So from this 70, my activated complex is going to have 70 kilojoules of energy plus another 50 added to it to reach 120 kilojoules. So I'm going to make the top of my bump be at 120 kilojoules. And this is where my activated complex would be. Then I know that there is a negative delta H. If there's a negative delta H, that means that this is an exothermic reaction. And I know that I need to lose 30 kilojoules of heat. So if I'm starting at 70 and I need to lose 30 kilojoules of heat, you could even do the reaction like the equation. You could go delta H is equal to heat of products minus heat of reactants. So if I wanted to solve for the heat energy of the products, it would be the enthalpy change plus the heat of reactants. So it would be negative 30 plus 70, which is going to turn out to 40 kilojoules. That is my cat clawing my chair. Cat, go away. Okay, so then I'm going to make this activated complex. It's going to drop down to 40 kilojoules, and that is where my products are going to go. And then the two things I'm going to make sure that I label, you can label more, but I'm going to label my activation energy. So it's the difference between my reactants and my activated complex. So I'm going to put energy of activation is 50 kilojoules. Now it says 50 kilojoules per mole because you would need 50 kilojoules for every mole of the reaction that's going to happen. Okay. And then the other thing I want to put is my delta H. So again, it is heat released. So some people like going like this and talking about delta H over here. And they would say delta H is equal to negative 30 kilojoules per mole. Or if you wanted to, you could put it over here, right? I don't really care where you put delta H as long as you have delta H in a correct spot going from reactants to products, and that it's covering 30 kilojoules. Awesome. Let's look at the next example. Next example says the following reaction has an activation energy of 167 kilojoules. 28, so the reaction is 28 kilojoules plus hydrogen gas plus iodine gas is going to, I want to say hydroiodic acid, or is it just the iodic acid? Those are the acids are always the tricky one for naming. I had to go look it up. It's hydroiodic acid. Okay, perfect. And it's not even an acid. Well, it's instead of gas. Okay, anyway, doesn't matter. What we want to look at is which of the potential energy diagrams is going to represent this reaction. So the two key things is that we're looking for a reaction that has an activation energy of 167 kilojoules and has a delta H of negative 28 kilojoules. Sorry, positive. Because this 28 kilojoules is a reactant, then we know that it's going to be an absorption of energy, which is going to make this an endothermic reaction. So the first thing I would do, since this is a multiple choice question, is I would eliminate all of the exothermic reactions. So I'm going to eliminate B because it's a step down, and I'm going to eliminate D because it's a step down. So now I'm choosing between A and C. Now, right off, when I look at C, this is the difference between the reactants and the activated complex. So for this one, there is an activation energy of 195 kilojoules, and I know I wanted an activation energy of 167, so I know it can't be C. Now let's just for sure make that sure that A is correct. So first things first, it's endothermic. There would be an absorption of 28 kilojoules of energy. So if I was to look at this one in terms of its activation energy, if there's 28 that's absorbed and the difference between the activated complex and the products is 139, then the activation energy over here is going to be the sum of 139 and 28, which is going to be 167 kilojoules. So I'm for sure picking A as my answer. Now, two follow-up questions. First one being just as a sort of reminder of some of the stuff we've already covered. First one is, which is the fastest endothermic reaction? Which is the fastest exothermic reaction? And how could you tell? So how can we determine which is going to be the fastest? Well, you're going to be looking for the one with the lowest activation energy. So let's look at the two endothermic reactions here. This one has an activation energy of 167 kilojoules, and this one has an activation energy of 195. So A is going to be the faster endothermic reaction. Pause the video, see if you can figure out which one would be the fastest exothermic reaction. So for this one, I mean, if you just look at these two, this one definitely, like this is the activation energy of this guy. It's going to be that 28 kilojoules. Whereas this one, we don't necessarily know which one it is, although we do kind of guess that they're kind of fooling us into knowing that this is 28 kilojoules in here, which would make this one have an activation energy of 100. Ooh, what's 167 minus 28? 67 minus 28. This one would have an activation energy of 139 kilojoules, which is much greater. So D is going to be the fastest exothermic reaction. Awesome. So that's the end of 1.10. Go and practice the questions.